Hello, everybody. Welcome back to Mathematical Statistics. When we last left off, we were talking about convergence and distribution. This was our second form of convergence for a sequence of random variables, x1, x2, x3, etc., to a random variable x. Now, we first had convergence and probability, which talked about the distance between the random variables and the fact that the x's were getting closer to x in some sense using an epsilon. But for convergence and distribution, the random variables are not getting close in any sort of sense. It's their distribution that's getting close. So it's really a much weaker statement to make about random variables in a sequence converging. It's also known as a weaker form of convergence than convergence and probability because we did show that if you have convergence of a sequence of random variables to a random variable x in probability, then you most definitely have convergence in distribution, but not the other way around. We saw an example of the other way around not working. So for that reason, convergence and probability is stronger, convergence and distribution is weaker. And if you're wondering about our weak law of large numbers, which involve convergence and probability, that's still known as weak convergence compared to a different form of convergence that we haven't talked about, known as almost short convergence. So where we are today is we're still talking about convergence and distribution. And so a quick two-line recap of what I just said. If you have xn converging in probability to x, this implies that you have convergence in distribution. And we did see that if you have convergence in distribution, this does not necessarily imply convergence in probability. Now here is the new thing. The new thing is that you can go back and forth with an if and only if kind of convergence if you are talking about convergence to a constant. So maybe xn converges in probability to some constant real number, little c. This happens if and only if xn converges in distribution to c. And this is great news for us because for us, our sequence of random variables is almost always a sequence of estimators. And it is hopefully converging to the actual fixed real number unknown parameter. So we are talking about convergence to constants, and we would like to get convergence in probability over distribution when we can because it's stronger. But if these are equivalent when you're talking about convergence to a constant, we could show convergence in distribution in order to get that convergence in probability result. And convergence in distribution tends to be easier to show. So that's why we love this new circled result. Let's prove it. We do already have one direction. We have the forward direction here just because convergence in probability to a random variable, even if that random variable is a constant, always gives us convergence in distribution. So if we want to prove this, let me just say that this forward direction is done. It's just a special case of what I have circled at the top of the screen. So let's prove the other direction. Let's suppose we have convergence and distribution and we want to show convergence in probability. So we're going to need epsilon. I'm going to let epsilon be greater than 0. As for some notation, I'm going to let fn of x be the CDF or cumulative distribution function for x. And I am going to let just capital F of x without an n be the CDF for the limiting random variable, which is a constant here. So this is the CDF for c for a constant. And we know what that looks like. Here is a number line. Here is the constant c. So if you want to look as like a function of x, like at the probability that x is that c is less than or equal to x, that is not happening down here, but it's definitely happening up here. So the CDF, or this constant, is going to be a flat line here at the height of 0. And then at c, there's going to be a hole here, and it's going to jump up and be right continuous and be filled in at a height of 1. And it's going to stay at the level 1 thereafter. So this CDF for c looks like 0 and 1. It's going to be 0 if x is less than c, and 1 if x is greater than or equal to c. So I am assuming, we're trying to show this direction. So we are assuming that this holds convergence and distribution. And that means we're assuming that the limit of this is this. And we're trying to show convergence and probability. To show convergence and probability, let's consider this particular expression because there's a few ways we can write it with inequalities flipped. I'm going to look at the probability that the distance between xn and c is greater than epsilon. So recall that when you're talking about a variable, random or otherwise, like a lowercase x in absolute value being greater than 3, this means that either x is greater than 3 or that x is less than -3. And if x is a random variable, these are disjoint events. You can't be both greater than 3 and less than -3. So for disjoint events, you get to add 2 probabilities. And so coming back over to this probability up here, I'm going to use this and rewrite this as xn minus c greater than epsilon and drop the absolute value plus or the probability of the disjoint event where xn minus c is less than -epsilon. I do know things about the CDF for the xn, so let me try to isolate the xn and these inequalities so that I can write these things in terms of CDFs. This first one is the probability that xn is greater than c plus epsilon, and the second one is the probability that xn is less than c minus epsilon. So the first term is 1 minus a CDF. This probability is 1 minus the probability that xn is less than or equal to c plus epsilon. What we're doing right now, this claim, this new thing, this is true even if we're talking about a sequence of discrete random variables. And when things are discrete, inequalities do matter, at least for rewriting things in terms of a CDF. So this is not the CDF. We need a less than or equal to there. It won't matter if we are talking about continuous random variables and a continuous random variable sequence. But if they are discrete, we do need to take care of this before we can rewrite this as a CDF. So I am going to make this a less than or equal to. And if you think about it, being like less than the number 3 versus being less than or equal to the number 3, that second event is going to have higher probability because there's more possibilities there for you to achieve that event. In other words, I am going to get something greater if I replace the second term with what I've written there with the less than or equal to. So now, this over here, this last term, is the CDF for xn evaluated at c minus epsilon. And then the first term is 1 minus the CDF for xn evaluated at c plus epsilon. So we got this line. I think we're ready to take a limit. I'm going to take the limit as n goes to infinity of the probability that the absolute value of xn minus c is greater than epsilon. This is less than or equal to the limit as n goes to infinity of 1 minus blah, 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 epsilon. And because the xn's converge in probability to x with corresponding CDFs, fn and f, I do know that these fn sequences converge to capital F of c plus epsilon and c minus epsilon respectively. So this is taking the limit 1 minus capital F of c plus epsilon plus capital F of c minus epsilon. And this is since xn converges in distribution to x. That is the assumption for this part of the proof. So let's go back up here and check out our CDF for c. Let me remove this other part. So in this CDF for c, if we look a little bit to the left of c, like c minus epsilon, the CDF evaluated there is going to be 0, whereas if we look a little bit to the right at c plus epsilon, the CDF evaluated there is going to be 1. But back down here, this is 1 minus 1 plus 0, which is 0. So we have the limit of the probability we care about being less than or equal to 0, but because it's a probability and only takes on values between 0 and 1, we have shown that the limit of the probability absolute xn minus c being greater than epsilon, this must equal 0. And that is one of several ways we show convergence in probability of xn to the constant c, which is what we wanted. So again, this is great news for us. Our sequence of random variables is going to be a sequence of estimators, and we always care about it going to a constant and not random thing, which is the unknown parameter theta. Okay, so next up, we have the continuous mapping theorem. You've seen this before for convergence in probability, and it also holds for convergence in distribution. And so I'm just going to state it for both so that we have those statements in one place. If we have a function g from the reals to the reals, if this is continuous, yes. Number one, if xn converges in probability to x, this implies that g of xn converges in probability to g of x. And we've already proven that at least when x was a constant. And the full proof is not actually that much worse. And now I'm adding a new statement, which is the same thing, but with d's over the arrow. So if xn converges in distribution to x, then g of xn is going to converge in distribution to g of x. And this is our new result. So they're both known as the continuous mapping theorem. And we're going to see even other types of convergence going through continuous functions like this. And so we can add on to the continuous mapping theorem. Now, proving this one with convergence and distribution is really hard or really technically hairy. It would take us a very long time, probably at least 2 lectures. And so we don't want to do it. And I really hate stating results without proof. I do it infrequently. And I think the majority of the times I'm going to do that in this course are going to be today, because there's something else in here we won't prove today. But then we'll get back to being rigorous next time. So I am going to ask you to believe this. If you do want a reference, one of my favorite sort of Bibles of measure theoretic probability is by Patrick Billingsley, and it's known as Probability and Measure. And I like that as I said, like sort of like the go-to, but I also have a lot of other books to recommend to you that I think are a lot easier to read. So shoot me an email if you want my opinion on that, but otherwise I'm just going to press on. Okay, so here is an interesting thing. You may recall the first time we saw that continuous mapping theorem for convergence and probability, there was not a lot of fanfare. It was really just property 4 in a list. And in that list, I was sort of making a joke where I said, xn converges in probability. Now, I'm not going to write that because I do want this to be a distribution statement. But I wrote xn converges in probability to x, and yn converges in probability to y. And I said, this implies, and I was kind of almost joking, right? Like, what could this possibly imply about the sum? This implies that the sum converges in probability to x plus y. Like, how surprising is that? But I really shouldn't have been so flippant with that because it's actually not true when you have convergence in distribution. I know that doesn't feel good, does it? The reason is, again, that it's not really about the random variables getting close, but about their distribution getting close. So let me give you an example. Suppose we have x1, x2, etc., IID, independent and identically distributed, normal, 0, 1, random variables. And suppose I have x, also normal, 0, 1, independent of the sequence. So we have kind of trivially, this implies that xn converges in distribution to x, because that means that the CDFs for these, as n goes to infinity, approaches the CDF for this. But nothing's moving here. The CDF for xn is the probability that xn is less than or equal to x. And this does not depend on n, because it's not like I have a normal 0, 1 over n distribution or something. They all have the exact same distribution. So they all have the exact same CDF. And I will be bringing this notation up later, but if you've had other statistics courses, you might be familiar with like a capital C. The standard normal distribution is so important in statistics that it gets its own letter as opposed to a capital F, but there's nothing wrong with using a capital F. There is a CDF here though, and it is the same for x1 and x2 and x3. And when you take a limit, it's not changing. It's like taking a limit of the sequence 3, 3, 3, 3, 3. That limit is 3. So that's why we get convergence in distribution, because this also has the same CDF. If you're taking the CDF and then the same CDF and the same CDF, same thing, and it's approaching the same thing. That's why we have convergence in distribution without having to show very much. Actually, the normal distribution, as ubiquitous as it is kind of nuts that we can't write down this CDF in a closed form way, but we'll get back to that. We're not doing normal distribution stuff today, just a little bit in this example. But it was supposed to be an example of this line that's now at the top of the slide, holding, or the implication not holding. So I'm going to let for n equals 1, 2, 3 on up, I'm going to let yn be the negative of xn. So we know that y1, y2, y3, or we can be easily convinced that because the normal 0, 1 distribution is symmetric about 0, if you take a negative of it, you still have a random variable with the same distribution. For example, for a normal 0, 1 random variable, the probability that that variable comes out between 1 and 1.2 is the same as the probability it's between negative 1.2 and 1. So you get, like this bell curve. And if you imagine observing the random variables, they'll come out all over the place. But if you take each one of these little x's and flip it over the y-axis where x equals 0, you're going to get the same sort of distribution of things. So for this reason, these negatives of these normal 0, 1s are also independent of each other and normal 0, 1. So yn converges in distribution 2. Now here's where things can get a little weird. Convergence in distribution is not about getting close to a specific random variable. So I can say with certainty here that it's going to converge to a random variable y, where y is normal 0, 1. And we don't need y to be specifically the negative of x. Really, when you're talking about convergence and distribution, you're kind of not talking about a limiting random variable at all. These circle things are just formal ways to write down like yn converges in distribution to a normal 0, 1. But this y doesn't have to have anything to do with these y's or these x's or this x. So it doesn't have to be the negative of x. And so what do we have here? The way we define things, xn plus yn is always 0 for n equals 1, 2 on up. And so xn plus yn as a sequence is going to converge in distribution and probability in any other sense to 0, or to a random variable that's equal to 0 with probability 1. Whereas the x plus y that I've defined here is going to have some kind of normal distribution. I have two normal 0, 1s, and if I assume that x and y are independent, I will get a normal 0, 2, because the variance of x plus y is the sum of the individual variances if they're independent. But if y is negative x, you don't get a normal. You get something that's 0 with probability 1. Or this y could be defined to be some normal 0, 1 that has some sort of correlation with x, in which case when you compute the variance of x plus y, you'd get the variance of x plus the variance of y plus 2 times the covariance of x plus y, which could be some actual non-zero number, which is going to change this variance. So there's several possible outcomes for how we can define both of the individual limiting random variables and how they are related to each other. Are they independent? In which case, the variance is just going to sum nicely. There's a lot of ambiguity here. And the reason is that we can't really talk about functions like this converging in distribution unless we know something about how they are moving jointly. So let me back up to the continuous mapping theorem here. I did say in the last class that for proving, or maybe the one before, one of the last two, that for proving things like xn, yn is converging in probability to x times y, you could do that with brute force and inequalities, but the best way I think to do it is to put them through a continuous function, like g of x and y is x times y. And that's how you can get results like this out of the individual x's and y's converging in probability. We haven't shown it in here. I am going to put this as an extra write-up on Canvas, that joint convergence in probability, which involves a sort of very similar statement to what we've seen, but the absolute value turns into a Euclidean norm, is actually equivalent to the individual components converging in probability. So you can go both ways with that. Joint convergence in probability gives you individual component convergence in probability and vice versa. So you might be thinking, why can we not pull this off? Like maybe even with more specifically gxy equals x plus y with convergence in distribution. The reason is that joint convergence in distribution, which I'm going to define for you in a second, does not happen. It's not equivalent to the individual components converging in distribution, like it is in the case with convergence in probability. So that causes a problem. But overall, the bottom line is for us to be able to talk about functions of thing converging in distribution, moving through functions, we do need to know something about how their distributions are working together, if they are at all, jointly. So let me try to write that down here. We're not going to use too much of this, but we do need it. We do need it right now to prove a very exciting upcoming theorem. What? Joint convergence and distribution. So usually convergence and distribution is about CDFs, and this is about joint CDFs. So we're going to say the limit as n goes to infinity of the joint probability that xn is less than or equal to x and comma yn is less than or equal to y. This needs to go to the joint probability that x is less than or equal to x and y is less than or equal to y. In this case, we write xn, yn as a vector converges in distribution to x, y, or maybe you'll see this written as like a zn converges in distribution to z, where zn has been defined to be a two-dimensional random vector. So this does not happen if you have this converting to this and separately this converting to this. That's kind of the problem that we've been talking about for the last 10 minutes. But if you have joint convergence in distribution, you can apply the continuous mapping theorem. And so if you look at g of xy being x plus y, then x and yn converging jointly in distribution to x, y will imply, via the continuous mapping theorem, that xn plus yn is converging in distribution to x plus y. again, with the previous normal example, I didn't know enough about what was going on jointly with the X and the Y, the limiting random variables. Okay. So again, you cannot get this out of marginal convergence in distribution. I'm going to write this, I guess, again. Lillian trying to drive something home here. If you have convergence in distribution for two sequences, you do not necessarily have convergence in distribution for the sum or the product or other, like G of xn, yn is not necessarily going to converge in distribution. You do need something joint to happen here. So you do need this to happen. And what I care about today in particular is a special case, which is kind of like, I was talking about with our limiting random variables always being constant. This is a special case that is really useful to us in mathematical statistics. So this is the one we're going to focus on. My claim is that if xn converges in probability to a constant a or c, and if yn converges in distribution to a random variable y, which could be a constant or not, then I claim that we're going to prove this, that xn yn is converging in distribution to a y. If this was a d, or if this was not a constant, we wouldn't necessarily have this result, but we do in this case. And again, this sort of case is going to be something that is really useful to us in MathStat. So let's prove this claim. And then after we prove this claim, we can talk about things like this for our sequences of estimators. Okay, so let's prove it. So I don't know if I need to write this, but I'll write it for completeness. Suppose that xn converges in probability to A and yn converges in distribution to y. I am going to let f sub n of x and y be the joint CDF, the probability that xn is less than or equal to x and yn is less than or equal to y. And I want to show that this converges as n goes to infinity to the joint CDF for A, the constant, and the random variable y. So let's define that. I'm going to let capital F without an n of x and y be the probability that little a is less than or equal to little x and the random variable y is less than or equal to little y. So this is a very weird statement because there's nothing random over here. So this is like, we've seen this before. It's like talking about the probability that x is less than or equal to 3 and 1 is less than 4, something like that. 1 is always less than 4. So this is just the probability that x is less than or equal to 3. This is just irrelevant. Whereas if you have the probability that x is less than or equal to 3 and 1 is greater than 4, this event is never going to happen because this part is never going to happen. And the event in parentheses here means both of those things are happening, but this can't happen, so this is a 0. So that's what I'm about to do with the line that's on the bottom now. I'm going to rewrite this kind of piecewise as just the probability that y is less than or equal to y if, in fact, a is less than or equal to x, and then 0 if a is greater than x. That is CDF for this random vector. Okay, I want to show that this, as n goes to infinity, converges to this. And remember, for convergence and distribution, we only need the convergence to whole at all points of continuity of the limiting CDF. So I'm going to let, maybe, I don't know, that's capital. I'm going to make it a little more curly so it'll like a constant. Whatever, we're not really going to need this letter. I'm going to let this be the set of all points of continuity. And the CDF for y, the probability that y is less than or equal to y. Because this CDF here has a discontinuity as x moves from less than or equal, as x moves from less than a to greater than or equal to a. But it also might have points of discontinuity up here as well. And so I'm going to then define all of the points of discontinuity. And they call this like, I don't have letters. I'm going to call it D. I'm trying to make it kind of curly and large. But after this proof, we're not going to need this again. So I'm going to let this be all pairs x and y such that x is not equal to a and y is in C. This is the points. That doesn't look like points. This is the set of points of continuity of this limiting CDF that is currently at the top of the screen. And these are the only points we need to consider when showing that this is moving towards this. So there is a sort of breakdown here when x equals a. So I'd like to consider two cases. I actually don't want to consider when x equals a because that's a point of discontinuity. So I want to consider when x is less than a and when x is greater than a. And in both of those cases, if I can write down an expression for this CDF and take a limit and get this, then we're done. So let's do the x less than or a case first. I guess above this, I should take a point that we're going to look at. So take any x, y in this set D. We want to show that the limit of fn of xy is f of xy. And now I'm going to go into the case where x is less than a versus greater than a. The CDF, the joint CDF, is the probability that xn is less than or equal to x and yn is less than or equal to y. That's just the definition of the joint CDF. I am going to drop, this event has to happen and this event has to happen. And if I drop one, that's going to make the whole event easier to happen. In other words, I will get a larger probability if I drop either one of those, and I am going to drop the yn one. Right? It's easier to say if you're rolling a die and flipping a coin, what's the probability you get an even number on the die and heads on the coin versus the probability you just get an even number on the die. It's easier for that one thing to happen than it is for both things to happen, so you get a higher probability. And so now I want to use the fact that I do know that xn is converging in probability to a, and I'm going to start rewriting this. I'm going to say xn minus little a is less than or equal to x minus little a. And the way I have this, because we're in a case where x is less than a, this is a negative number. So this is less than or equal to the probability that xn minus a is less than or equal to x minus a, plus the probability that xn minus a is greater than or equal to a minus x. Why is this line bigger? Because I threw in another probability, and probabilities are always greater than or equal to 0. And I threw in the one that is going to combine with the first probability to get that absolute value back in there. So this line is equal to the probability that xn minus a is greater than or equal to the a minus x term. I do have to take the positive one of these two numbers. And I'm in the case where x is less than a. So again, this line is larger than this line just because I added another probability, which could be 0. I did say it's greater than or equal to the previous line. But now I'm down to something that looks like something we can work with if we know that xn is converging in probability to a. This is like your epsilon, right? A has been fixed by the problem. X has been fixed up here. We started the proof. We took a point. So this a minus x is just a number and call it epsilon. Look at the limit as n goes to infinity of the joint CDF for the xn and the yn. This is less than or equal to the limit as n goes to infinity of this probability. And again, this is a fixed positive number. And because I forgot my n on my xn, because xn is converging in probability to A, it will not be greater. That distance will not be greater than this number with any positive probability. So this is going to go to 0 since xn is converging in probability to A. And so we have another kind of squeeze result. This is, the CDFs here, these are probabilities. These are between 0 and 1. They can't get negative. So this implies that the limit as n goes to infinity of fn of x, y is 0. We are in the case where x is less than A. And in the case where x is less than A, the limiting CDF is supposed to be 0. So let me erase some of these. I have way too many circles on here. So one more time. We are in this case. We took this and we showed as n goes to infinity, it goes to this. So we do have this approaching this when we're in the case where x is less than A. So we're halfway done with this problem. Let's do the other side. So now let's look at the other case, the case where x is greater than A. We want to look at when x is equal to A because that's a point of discontinuity for the joint limiting CDF. I'm going to start out a similar way. I'm going to start out with the joint CDF of xn and yn. By definition, this is the probability that xn is less than or equal to x and yn is less than or equal to y. And this time I am going to drop the opposite term in here. This is less than or equal to the probability that yn is less than or equal to y. Ooh, that's what I want the limit of this to actually equal. And actually, that's not it, but we can take a limit at this point. The limit as n goes to infinity of fn xy is less than or equal to the limit as n goes to infinity of the probability that yn is less than or equal to y. And this is the probability that y is less than or equal to y. And this is since yn is converging in distribution to y. That was part of the setup of the problem. So I've got this thing that we care about, its limit being less than or equal to this thing, but I want it to be equal. So now I'm going to rewrite this top line and drop something else in the right way so that I can get the limit to be greater than or equal to. So I want to get this greater than or equal to this, and that would force them to be equal. So let's do that. Let's look at, again, fn xy. This is the probability. Xn is less than or equal to x, and yn is less than or equal to y. You might try to drop the other term, and leave the xn. It's not going to work. Believe me, the first time I proved this, I tried many things. So what ends up working for me is the fact that, let me just give this its own line and I'll erase it because I don't really have room for it. If you want to find the probability that y is less or equal to y, you could drag in another event and the complement of that event. So this is the probability that yn is less or equal to y and xn is less or equal to x, or plus adding that disjoint event probability, y is less or equal to y and xn is greater than x. Of course, I can write these in the other order, and I will. But this first thing is this right here. So taking the line from the bottom, I can go back up here and rewrite this as the probability that yn is less than or equal to y minus the probability that xn is greater than x and yn is less than or equal to y. Let me let that sink in for a second before I erase that there. I am trying to get the fn on the larger side of something so that when I take a limit, I can sort of, right now we have this limit is less than or equal to this, and I'll be getting greater than or equal to that. So I'm going to erase this fun fact just to make it a little cleaner here and go back up to where we were. I am going to, I'm going to drop this guy. If I drop this out of this probability, I look at something that has a larger this probability will become larger, but I'm subtracting it. So overall, this next line is going to be smaller than the line above. This is what I have here is greater than or equal to the probability that yn is less than or equal to y minus the probability that xn is greater than x. This is kind of what I want to see, right? I want to take the limit of this and say it's greater than or equal to the limit of this. And I kind of want this to go away. So I'm going to pull the same trick as before. I want to use the fact that xn converges in probability to a to rewrite this. So this is equal to the probability that yn is less than or equal to y minus the probability xn minus a is greater than x minus a. And we are in the case where x is, it was supposed to be an exciting new color, that x is greater than a. And that means that, going back to this line, this is greater than 0. So if I replace that second probability with the probability that xn minus a in absolute value is greater than x minus a, this would be the probability that xn minus a is greater than x minus a, plus the probability that xn minus a is less than the negative of x minus a. So this is right up here. So if I were to put this in place of this, I would be subtracting something larger, which would overall get everything to be smaller. So this line is greater than or equal to the probability that yn is less than or equal to y minus this probability. When I put the absolute value on, I'm actually subtracting more stuff, making it smaller than the line above. But I know you see where this is going now. This is like your epsilon. It is positive. And now I'm going to take the limit as n goes to infinity of fn of x and y. This is greater than or equal to the limit as n goes to infinity of this line, just one line above. The first limit is the probability that y is less than or equal to y, because yn is converging in distribution to y. And the second limit is 0 because xn is converging in probability to a. So this is since yn is converging in distribution to y, and this is since xn is converging in probability to a. So we have this limit is greater than or equal to this. And before, that's a mess. Check rid of these lines. But before we had that, this limit is less than or equal to this. So putting them together, we have that the limit as n goes to infinity of fn of x and y is equal to the probability that y is less than or equal to y. And this is our limiting CDF, at least when x is greater than a. So we're done. Our limiting CDF was the probability that y is less or equal to y, and sometimes it's 0 when x is greater than or equal to a, and when x is less than a, and we have this point of discontinuity at a, and maybe others, depending on where the y's are, but we don't care about those. So we looked at all the x's strictly greater than a and all the x's strictly less than a, and we did get that this approached this when it needed to, and this approached this when it needed to, and therefore this is approaching this. And that is how we show that the vector x and yn is converging in distribution to the vector a and y, starting with the assumption that xn converges in probability to a and yn converges in distribution to y. That was really fun. It's going to be a super important result for us actually right now. We're about to head into something known as Slutsky's theorem, which is what you want to use whenever you are trying to combine types of convergence, like maybe an xn plus a yn, where one is moving in probability and one is moving in distribution. Slutsky's theorem is the way to go. And this result we just proved is key to proving Slutsky's theorem. So let's go. So suppose we have a sequence of random variables, x1, x2, x3 on up, that converges in probability to a constant, and I'm going to call it A. So xn converges in probability to A, and I'm going to suppose that we have a sequence of random variables, y1, y2, etc., that converges in distribution to a random variable y, which could potentially be its own constant, but it can also be a random variable. So then we have a few things. One is that xn plus yn converges in distribution to a plus y. The second is that the product converges in distribution to the product of a times y. And finally, the ratio yn over xn converges in distribution to y over a, provided a is not 0. So the first thing I want to point out here is that all of the types of convergence and distribution are the weaker type. We're combining a convergence and probability result with a convergence and distribution result. And the best we can hope for when we combine them is the weaker type of convergence. But these are some really useful results. And we have proven these if we believe the continuous mapping theorem, which we were not able to prove because we know, so it isn't really a proof, a one-liner here. If xn is converging in probability to A and yn is converging in distribution to y, we now know from the claim we just finished proving that xn, yn as a vector is converging in distribution to a, y as a vector. So now you would use the continuous mapping theorem on all of these, on 1 through 3. You know, for 1, you would let g of xy be x plus y. And you would use the fact that if this is converging in distribution to this, then you could put that step through a continuous function like this g, and you'll get that xn plus yn converges in distribution to a plus y. And the same thing for the other cases. So to prove the second one, you're going to just choose your g of x and y to be the product. And the third one, you're going to choose the function y over x. And if you have a problem with continuity here, maybe you do, but if xn is a random variable that has a continuous distribution, then you won't land on 0 with any positive probability. So this is likely not an issue. So this is, a pretty important theorem in mathematical statistics. It's going to get us a lot of results. Let's look at a couple of examples from last time when we were looking at convergence and distribution. So we had the example x1 through xn, IID, Pareto, with parameter gamma, where gamma is some positive constant. And we defined in one example yn to be n times the minimum of the x's, which also depends on n, because this is notation for the minimum of x1 through xn. And we went through the convergence and distribution process. We wrote down the CDF for this, and we saw, so we already know that n times this minimum is converging in distribution to an exponential distribution with rate gamma, or it's a little more correct to say that it's converging in distribution to a random variable x, where x has the exponential rate gamma distribution. So to show this, if you don't recall how we did it, we wrote the CDF down for this and worked our way down. And took a limit as n goes to infinity and got the CDF for an exponential with rate gamma. So then we did a second example with the same Pareto setup. And we wanted to investigate convergence in distribution of just the minimum alone. So I'm going to do this part differently now. Note that we can write the minimum as 1 over n times the minimum. And we can use the fact that we have just shown in the above example, actually referencing a previous example, that this converges in distribution to a random variable x, where x has this exponential distribution. And this sequence of real numbers here converges in probability to 0 as n goes to infinity. Remember, we have talked about convergence in probability when you just have a sequence of numbers. It's just kind of a trivial thing where all the relevant probabilities are all zeros or ones, and you need the limit to go to the right thing, depending on how you set up the inequality. So here, I've written this minimum as a product of things, one of which is going off in probability to 0, and the other which is going off in distribution to x, where x is exponential with rate gamma. So we have, by Slutsky's theorem, as a product, this converges in distribution to 0 times x, which is 0 by Slutsky's theorem. And this is a result we already knew. We showed it differently in the last class, but you can see that from one example of convergence in distribution, we can get lots of other results pretty easily without having to start all over. So this is an example of Slutsky's theorem. I did say that today was going to be the day of unproven claims. This next theorem is kind of in Laplace transform territory, which is outside the scope of the course. It says that suppose that x1, x2, etc. is a sequence of random variables, and I'm going to let capital F and X be the CDF for xn, and I'm going to let capital M sub n of t be the moment generating function for xm. So this is going to be the expected value of e to the t xm. Now I'm going to let x be another random variable with CDF capital F of x and its own moment generating function that I'm just going to call m of t. Or if you'd like, you could put the subscript x on both of these. But here is the point of all this. Then, if the limit as n approaches infinity of m n of t is equal to m of t, this is going to imply that the limit as n goes to infinity of f n of x is equal to f of x. And I do have a tiny bit more to write at all points of continuity, blah, blah, blah. But what this is saying is that if you want to show convergence in distribution, you could show convergence of moment generating functions, and it's equivalent. And basically the idea is a moment generating function is a function of the PDF, which can in theory be inverted, even though it's usually close to impossible to do in practice. Given a moment generating function, you can determine the exact PDF, and you can therefore determine the exact CDF. And so you've got this correspondence here where if the moment generating functions are converging, so are the CDFs. And I do have to say something again about points of continuity and stuff, but really this is an if and only if result. I'm just not stating it that way because this backwards arrow will be only if these moment generating functions exist. They are expected values like this, and they could blow up and be infinite, and so you don't have a meaningful moment generating function. And that's the only time where you're not going to get convergence in distribution, implying convergence of moment generating functions if the moment generating functions just don't make sense. So mostly this is the next and only if. And just to finish it off, a technical thing here is over here on the right side, this has to hold at all points of continuity of the capital F. That's just part of our convergence in distribution. And this limit over here needs to hold for all t in some neighborhood of 0, meaning you have to be able to go a little bit on both sides. So if you have a moment generating function that only is only defined, and maybe it blows up the rest of the time, but it's only defined for t greater than 0, then that is not going to be enough. You need to be, this is your t-axis, some little neighborhood or big neighborhood, but you need to be able to go out both sides from 0 and have the expectations for defining these moment generating functions. You need those to be finite for some neighborhood around 0. So these are two technicalities, but for the most part, moment generating function convergence is equivalent to the CDF convergence. And this is good. This is good because a lot of times we can't write down CDFs in closed form. I was just saying it today. Even for the standard normal distribution, we don't have a closed form expression for the CDF, but we do have a closed form expression for the moment generating function. So let's look at one quick example, and then I think we're going to call it a day. So suppose that we have a sequence of random variables, x1, x2, etc. Suppose these are independent, but not identically distributed. I'm going to have the nth one, xn, have a binomial distribution with parameters n and. So usually the parameters are n and p, but I want the p to be changing with the index n, and I want it to be getting small. So the particular p I'm going to choose is like a p sub n, and specifically it's going to be a lambda over n toward some lambda greater than 0. And the n's are positive integers. So that is the setup. And right now, I'd like us to investigate the convergence in distribution. When I say that, it's because I'm not giving you the end. It's not like, show this convergence in distribution to that. When I say investigate the convergence in distribution, it means right out of the CDF, take a limit and see what you get. And we won't just look, actually, we'll just look at xn. So xn, like what is this going in distribution to? That doesn't make sense at the end of the sentence, but that's the idea. So why am I doing this right now? We just talked about moment generating functions. The binomial distribution is discrete, and its CDF is going to look like a step function, and it's really quite messy to write this down. Remember, the binomial has combinatoric stuff in there, and the CDF is going to keep changing in n, and these steps are going to get closer and closer together with smaller and smaller jumps, but there really isn't a nice expression for the CDF or the binomial, which is why this is a good candidate for moment generating functions. So recall, just outside of the context of this problem, if you have a binomial np, then the moment generating function, which was the expected value of e to the tx, is 1 minus p plus p e to the t to the n. And you can just look that up in your table because it's not the point of the problem. If the point of the problem said derive the moment generating function from scratch, then no, you should not just look it up in the table. And if you look it up in the table, you'll notice that there's no restriction on t. So this holds for all real numbers t. I'm going to make this parenthetical. This is a total aside, and I don't want to get confused with the limiting x here. But let's use this fact to write down the moment generating function for xn. the moment generating function for xn is, I'm going to call it m sub n of t. This is the expected value of, actually, I don't need this, do I? It's a binomial. And instead of p, we have a lambda over n. So the moment generating function is just this, but in place of p, we have lambda over n's. This is 1 minus lambda over n plus lambda over n e to the t to the n. I'm going to let n go to infinity, but first I'm going to clean this up a little bit. I'm going to combine those last two terms in there and say that this is lambda times 1 minus e to the t over n, all to the nth power. We want to let n go to infinity. Which is the limit as n goes to infinity of this thing. Well, too lazy to write that. But you might recognize this limit. The limit as n goes to infinity of 1 plus x over n to the n is how we get e to the x. Right? The second term here is going to 0. So it's kind of like this is going to 1 to a higher and higher power, which you would think would be 1. But we don't quite hit that 1. So the higher powers are getting larger, but not that much larger. And the kind of balance here is that you get e to the s. Going back to our moment generating function, this is just going to be, if you have a negative here, so if you're looking at the limit as n goes to infinity of 1 minus x over n to the n, you, of course, can think of this as 1 plus negative x over n to the n, and that limit is going to be e to the minus x, and that's kind of more what we have going on here because of this negative. But this limit is e to the negative lambda 1 minus e to the t. And that is a fine answer, but if you're going to your table of distributions and trying to recognize this, you might want to turn this around, get rid of that negative. And this is, and I'm not saying you're supposed to have this in your head, so go to your table. This is the moment generating function for the Poisson distribution with parameter lambda. For us, this is just sort of a plug and chug kind of result. If you take this certain binomial setup and look at convergence and distribution, you go to a Poisson. If you have experience or are going to be taking a course in Markov chains or stochastic processes, this relationship is pretty important. And there you would get to talk more about the intuition about what's going on here. But for us, it's just a result. I guess I should finish this off and I should say, so xn converges in distribution to x, where x is Poisson with parameter lambda. Okay, next up on Thursday, we're going to be talking about the central limit theorem, the famed big theorem in statistics, which gives us some justification for using the normal distribution way too much. And the central limit theorem says that almost regardless of your underlying distribution for x1, x2, x3 on up, with a little bit of restriction, if you look at the sample mean x bar, as n gets large, x bar will start to have what looks like a normal distribution. And if you've had any statistics before, like a data-oriented course, you probably have used the central limit there. But did you know that that result is specifically a convergence in distribution result? And we're going to prove that next time. We're going to show it using moment generating functions, and we're going to do a lot of just manipulations with the normal distribution because it's so important in statistics. Next time on Mathematical Statistics.